Okay, we'll start back up where we left off on Friday, deriving the heat diffusion equation. So we basically wrote down that the heat diffusion equation is used to calculate the temperature distribution within an object if we know the boundary conditions and the initial conditions. And so we kind of drew out just a differential element with generic energy storage, change in energy storage, energy generation, and then heat coming in and out of all the surfaces via conduction. So you should have this in your notes already. And then we wrote down the generic form of the first law for heat transfer on the rate basis. So we've got dots on all the terms. And then we said we're going to assume that there's no bulk motion. So this energy in and energy out terms can be due to either work, heat, or advection. And since there's no bulk motion, we're going to assume that there's no work and there's no advection. Those terms are zero. So that leaves us with just heat being transferred in and out. And again, this is still consistent units because the small q is on a time rate basis. Okay. So again, we're assuming that there's no bulk motion, so we're just talking about conduction here. So we've got the Q in and Q out on every side. Let's see if I can scoot this out a little bit. There we go. Okay, so what we're going to do now is basically just figure out how to write generic expressions for each of those terms that are in the first law. So we'll start with, let's see, okay. Sorry, we'll have expressions for each term. And we'll start with the heat flux via conduction out of the element. So this qx plus dx, y plus dy, and z plus dz. We need to be able to express that in terms of kind of other variables. So since this is just a change over an infinitesimally small distance, we're going to say that the conduction rate leaving the element is equal to the conduction rate entering the element plus the change in that rate, so the partial differential with respect to x, multiplied by the distance that it's moved, or the distance of the element. So this is basically saying at the exit you have the heat rate at the inlet plus however much that's changed times the distance that you've gone. So you end up with kind of just like a small change from your initial q sub x. And this can apply to y and z as well. So you have the same expressions, just x replaced with y and z. Okay, for the energy generation term, we're just going to represent that as q dot, so heat occurring inside, or heat being generated at a certain rate inside the element, times the volume of the element. So the volumetric heat generation. And this q dot here, so you have a lot of q's and dots floating around, that's watts per meter cubed. So then if you multiply by meters cubed, the volume, you get just watts. And then finally, the energy storage term. We've got, so last time we talked about the change in the energy storage being expressed by this rho Cp V delta T. And since we're talking about it on a time rate basis now, E dot, it's rho Cp times the partial derivative of the temperature change with respect to time times the volume of the element. Dx, dy, dz. Okay, so now we have expressions for each of the terms in this form of the equation. So we'll just plug them all in. Let's see, start on a new sheet here. So again, starting with this form of the first law that we've kind of simplified down by making these assumptions about the lack of bulk motion in the system. And then we wrote out expressions for each of the terms. Now let's just plug those in. So the energy storage term on the left, and then Q in and Q out, that's going to be from all three directions. So we have to include the energy due to X, Y, and Z, conduction in the X, Y, and Z directions. So those are the inlet terms. And then the outlet terms, which get subtracted, are the X plus dx. Sorry, that should be a minus. Y plus dy and Z plus dz. So nothing particularly new here, just plugging in all the expressions that we derived. And then finally, the energy generation. So we, earlier on, we derived the expression for Qx plus Bx right here. So we'll just plug that in and do a little bit of simplifying that I'm not going to explicitly show and get kind of a simpler form of the equation. Very easy simplifying, just subtracting out terms that are repeated. Sorry, that should be a partial on the bottom. Okay, and we know an expression for Qx, Qy, and Qz, right? From Fourier's law. So we can express Qx, y, and z in terms of Fourier's law, which we learned previously. Negative Ka times the partial of t with respect to x. And then again, same for y and z. And then here, instead of having the area, we're going to express it as the differential face of the element. So for the x direction, conduction is moving perpendicular to the kind of dy dz face. So it's moving in the x direction. And so the area that it's moving through is that differential element dy dz. So then rewriting that, and again, you can repeat that for y and z, where you just have the differential element being perpendicular to the direction of motion. And then if we kind of take all of those terms and substitute them into the form of the heat diffusion equation that we had and simplify it, we get the general form of the heat diffusion equation that we'll use. And because if you look back up here, because we're taking the partial derivative of the q, x, y, and z terms, and those have a partial derivative in them from Fourier's law, we're going to end up with a second order derivative in our general form. And then I'll draw a nice giant box around this, because it's fairly important. Okay, are there any questions on how we got to that? I think it's important when you're kind of like going through all this math to, when you're finished, take a step back and just kind of recap on what you did. So we started with a generic differential element, heat going in, heat coming out, and we made some assumptions about there being no bulk motion in the system. And then we basically just applied the first law. So this came up with some expressions based on what we know to plug into the first law. So this is just kind of another expression of the first law. So to have some kind of intuition on what these terms all mean. So these first three those are related to the net heat flux via conduction. And then this term is related to the energy generation and then energy storage. Which, if you think about the first law, that's exactly what we have, basically all the components of the first law. So the heat going in and out, the energy generation, and then the change in the energy storage. So this equation, this is a differential equation, right? And if you kind of look at what, basically what the what you're taking the derivative of in each case is the temperature with respect to the three spatial variables, x, y, and z, and then with respect to time. So if you solve this differential equation, you can get out the temperature distribution as a function of x, y, z, and time. Okay. And that's really helpful because once you have the temperature distribution, you can then take the first derivative of that, plug it into Fourier's law, and then you have the heat flux. So we can write that down, solving this differential equation. Gives the temperature distribution. And then dt dx, or whichever variable you're interested in. Plus Fourier's law gives the heat rate and the heat flux. And this is what's known as kind of the standard approach to solving conduction problems. You find the temperature distribution via the heat diffusion equation, take the derivative of it, plug it into Fourier's law, and then you have the heat rate. Okay, let's now go over some simplified forms of the general form of the heat diffusion equation. We like to make assumptions and cancel out terms to make our lives easier. So, let's see. Kind of three that are pretty important and that we'll use in this class. So standard assumption, we'll assume that we have constant K. Remember, that's the thermal conductivity, so the material property. So we're basically assuming that the material is isotropic, so the thermal conductivity does not vary does not vary spatially. And then that allows us to write the equation like this. Let's see if I can pull kind of the generic equation back up here. Yeah, so we can compare directly. So we're just pulling K out, and then we'll divide by it. And if you remember, this alpha here is our thermal diffusivity term that we talked about previously, and that's from dividing this rho Cp by K. Yes?
So is there no Z term in that? Or
Oh,
I don't see it.
yeah, sorry. This is a Z. I'll try to write a little clearer.
Oh,
I always like cross my Z's so that they don't get confused with 2's. Yeah, so that's a Z. Yeah. And these are all partials. Those little squigglies. Okay, any other questions? So the isotropic form, there's also steady state, which everything we've done so far, we've assumed steady state, so we're assuming no variation in time. And going through here, I'm just going to take the general form and then apply one assumption to it, but you can obviously combine assumptions and then have, a much more simplified version. So we'll have our K inside the parentheses here because we're back to assuming that it's not isotropic, and we're just assuming steady state. And then the only time dependence that we have is this last term. And so that's just going to be set equal to 0. So this is basically the same as the general form, except the energy storage term is 0. There's no change in the rate of energy storage. Okay, and then for the last one, we will combine some assumptions. So we're going to say it's one-dimensional. Steady state. And that there's no energy generation. So this is going to be a super simplified form. And because it's one-dimensional and steady state, the temperature is only changing with x. So one-dimensional cancels out the y and z terms, and then steady state cancels out the time dependence term. So we can write it as a full derivative because it's only dependent on one variable, x. And in general, going through homework and problems, I think it's helpful to start with, I may require you to do this, but even if not, it's helpful to start with the general form of the equation and then say why you're canceling out each of the terms. It's easy to, if you come across a problem, you just grab one of these different forms of the equation, and you don't really think about the fact that we've already made some assumptions that go into these forms of the equations. And if those assumptions are not applicable to your problem, then you're going to end up with the wrong answer. So it's best to start back with the general form, the boxed one, and then go from there. Any questions? Does everyone see how we got from here to here on all of these? Okay. So these equations are not super helpful. You can't directly get the temperature distribution just from looking at this. So they're differential equations, and we have to solve them in order to get the temperature distribution. And to do that, do you all remember what you need for solving differential equations? Initial conditions and boundary conditions. So we'll talk about some common boundary conditions that we'll be using. So there's kind of three main types of boundary conditions that we use in heat transfer. The first one is called the Dirichlet condition. And that's also referred to as a boundary condition of the first kind. And for those, basically the surface is just maintained at a constant temperature. So pretty straightforward. We'll call that temperature T sub S. And then specifying the boundary conditions mathematically, we're just going to assume a one-dimensional system and assume that we're applying the boundary condition at x equals 0, but it could be applied at, x equals L or some kind of different surface. And it would be the same if it was, just one-dimensional in the y direction. So this is saying that the temperature at the x equals 0 location for all time is T sub S. So that makes sense with having kind of one surface maintained at a constant temperature for all time. And in that case, it's the x equals 0 surface. So kind of realistically, this boundary condition can occur when a surface is in contact, for example, with a melting solid or a boiling liquid, because you have energy being transferred still, but the temperature remains the same. Okay, the second kind is the Newman condition. And that's when you have a constant heat flux at the surface. So instead of a constant temperature, there's a constant flux. So that's expressed as the heat flux at this surface, x equals 0, which we know the definition for heat flux, right? Negative k partial t partial x at x equals 0. And we're going to say that's just equal to this constant flux Q sub S. And then there's a special case of this condition, which is when a surface is perfectly insulated. So then the heat flux is constant and just equal to 0. Okay, and then there's one more commonly used boundary condition, and that is a convection boundary condition. And that's a boundary condition of the third kind. So we haven't talked about convection yet. We haven't really gone through and developed the equation for it. But we're going to get to that pretty soon, just kind of a brief introduction, because for conduction problems, you often have a surface that has conduction through it, but you've got fluid moving by the surface on both sides. So often conduction problems that you encounter are going to have a convection at the boundaries. So So you're going to have to know a little bit about convection to just be able to apply the convection boundary condition and kind of solve those problems. So for now, we'll just write down what this boundary condition is. So that can be convection heating or cooling. And so we'll say again, the heat flux at the surface is equal to the heat flux from convection. And this H is kind of a property that determines basically how quickly convection occurs. And then the T infinity is the temperature of the flow, so the fluid temperature. And then this T is the temperature at the surface. So again, at x equals 0 for all time. So this is just basically saying you've got convection occurring for all time at this surface, and that heat flux is going into the surface via conduction. So convection to the surface and then conduction through the surface. Okay, and like I said, we'll talk a little bit more about convection either today or Wednesday and have more of an idea of just how to apply it to solve the conduction problems. Okay, any questions on the boundary conditions? All right, now that we have some boundary conditions that we can use, let's try to solve a kind of very simple case of the heat diffusion equation. So we'll start with our really, really simple form. One-dimensional, steady state, no energy generation, and isotropic. So basically all the assumptions that you can make. And the equation for that form of the heat distribution is just this. And of course, you can divide both sides by k. So really, it's just the second derivative of temperature with respect to x equals 0. This is pretty easy to solve. We don't have to do any fancy differential equation stuff. We can just integrate it twice. So if we integrate once, we get dt dx is equal to some constant. And then if we integrate again, we get the temperature distribution as a function of x is equal to that same constant, the first constant, times x plus another constant. And note that we started with a second order differential equation in space, and we're ending with a equation as a function of that one spatial variable, but with two constants. So we need two boundary conditions in order to solve for the two constants. So second order differential equation, two boundary conditions in order to solve the particular solution. go back up here. A good example of this type of problem is just a plain wall. And you're maintaining both of the surfaces of the wall at 2 different temperatures. So surface temperature 1, surface temperature 2. You've just got one-dimensional heat transfer, and all of these assumptions apply. And then we'll have here x equals 0, and then over here, x equals L. So we want to plug in our first boundary condition. So if we write these mathematically, t at x equals 0 for all time equals t s sub 1, and t at x equals L for all time equals t s sub 2. So now apply the boundary conditions to this general form. So at x equals 0, and notice I've just dropped the t here because it's steady state, so there's no variation in t. And then we just get that C2 equals Ts sub 1. And then we'll plug in a second boundary condition. And then if we solve for C sub 1, we get the temperature difference between the two surfaces, divided by L. Give you a second to catch up on that. Pretty straightforward. Like the most simple differential equation you could solve. Does it make sense? So now we can go and plug these back into our equation. T as a function of x. And now we have something useful, right? So we have the temperature distribution, we just solved for it, in this wall, under the assumptions and the boundary conditions that we stated. So this is the temperature distribution given a 1D system, steady state, no energy generation, isotropic, and boundary conditions of the first kind. Okay, so a couple of the other boundary conditions involved a derivative, right? So to apply those, I'm not going to go through it specifically, but to apply those, I'll leave that up. You would need to apply the boundary condition after you integrate once. So you integrate once and you have the dt dx equals the constant. That's when you'll need to apply the other boundary conditions that are related to the derivative. Okay. Let's see. I'll write a note about that. So apply boundary conditions that involve a derivative after integrating once. And if you have, one boundary condition that involves a derivative and one that is just the constant temperature, you can apply the first one after integrating once and then the second after integrating twice, just whatever the appropriate form of the equation is. That's totally fine. You can combine the results to get what the constants are. So if you did this same kind of thing and went through and just instead of assuming that one side of the wall was held at a constant temperature, if you assume it was insulated, you just get the result that the temperature distribution is constant and equal to the temperature of that one surface, which again makes sense if you think about it, right? Insulated, and then you have a temperature at one surface. If you assume it's already at steady state, so everything's come to equilibrium, then you're just going to have that same temperature within the entire wall, because no heat is leaving through the insulated surface, so everything has just come to equilibrium. And you can work through that and see that that's what you get if you solve the heat diffusion equation. So it should all make sense. Okay, cool. Any questions on the heat diffusion equation? You can also derive this in cylindrical and spherical coordinates, which is a little more complicated. I think I might go through that in the recitation. I don't really want to take lecture time to do it, but I do want you to be able to work cylindrical problems. I thought about putting it on the homework, so you're welcome. For cylindrical at least. I don't think we'll go through spherical. But yeah, I want you to be able to work problems in cylindrical coordinates, but I want you to see the derivation if we're going to do that. And then I think we'll also do a little bit more practice, like applying boundary conditions and just solving the heat diffusion equation, so you can get kind of a better handle on how to do that. Okay. All right. Okay, in classic form, let's start a new topic with the 4 minutes left. Okay, as promised, we need to know a little bit about convection just so we can use it in conduction problems. You're going to often have convection on the surfaces, and you need to be able to just kind of deal with those boundary conditions. So we'll do kind of a small intro to convection. So the definition of convection is heat transfer between a surface and a moving fluid when they are at different temperatures. And it's important when you're talking about convection to differentiate between the kind of bulk macroscopic motion of a fluid and the microscopic motion, which we had talked about previously, which is just like the little atoms and molecules moving around. So there are two mechanisms that contribute to convection. The first one is just diffusion, which we talked about with conduction. So that's the energy transfer due to random molecular motion. And then on top of that, we have advection, which we've already talked about in the context of, mass flowing in and out of an open system. But advection is energy transfer due to the bulk or macroscopic motion of the fluid. So the fluid or the flow is carrying energy with it. Okay. So heat transfer due to convection is a superposition of these two mechanisms. So diffusion plus advection. Okay. So we'll talk a little bit more about convection on Wednesday and how it's related to what's going on in the boundary layer. And then continue with conduction problems after that. Thanks. See you tomorrow.
Thank you.